I'm happy to introduce David Berenstein, who will be the first chair.
Okay, thank you, Nathan. We're now going to have Matthias Gaberdiel and from ETH Zurich. He's going to tell us about the string dual of free and equal Fourier meals. Go ahead, Matthias.
Okay, well, thank you very much for the invitation. It's a great pleasure to be able to talk here. And I'm going to report about work I've been doing recently with Rajesh Kopakuma, but this really goes back to a series of papers that also involved other people, and I'll refer to these papers as we go along. So our basic aim is to try to prove the ADS-CFT correspondence. And in order to explain to you our strategy, let me remind you very basically of what the relation between the parameters on the string theory side and the dual CFT side are. So what's important in particular is that we're going to be at large n, as always, and then the TUF parameter, that's the effective coupling constant of the gauge theory at large n, is related to the radius or the ADS space in string units. So this is the key relation that will be important for the following. Now, in order to prove the ADS-CFT correspondence, if you really want to have both sides under control, you have to be in the weakly coupled gauge theory regime in order to have the gauge theory side under control. And this therefore means that the TUF parameter will be small, and as a consequence, the radius in string units will be small, and that's what's often referred to as the tensionless limit. That's the limit in which the size of the string is very, very large. It's as large as it can become, namely as large as the space in which it propagates. So this is what happens on the string theory side when you are at weakly coupled gauge theory. Now, this is the regime where ADS-CFT becomes perturbative or has a chance to become perturbative. And let me explain to you what I mean by this. So on the gauge theory side, we are weakly coupled, so that's clearly has a perturbative description. Now on the string theory side, as I've just explained to you, the radius will be very small in string units, or the string size will be very large. So you're very far away from the supergravity regime. So this is certainly not a regime that's perturbative from the supergravity perspective, but the idea is that the string theory side has some other redeeming feature that makes it into a tractable theory. And in particular, as has been long argued for, the dual of free super Mills should describe some theory with a higher spin symmetry. And in some sense, you should think of it as being the maximally symmetric phase of string theory. So our working hypothesis is that what makes this theory perturbative should also have some imprint on the string theory side. And the imprint on the string theory side should be that while supergravity is not easily describable, there should be something very simple about the worldsheet description corresponding to this very special background, namely to the one that describes free super Mills. And the idea, our basic working principle, is that this worldsheet theory will be free, or will be at least solvable, exactly solvable. There should be something that refers to the fact or corresponds to the fact that something very special happens on the gauge theory side. Now, this is our working hypothesis, and we have very good evidence that this is indeed how it works out, at least for the example of ADS3 cross S3 cross T4, where we have a very detailed analysis. And let me briefly remind you of what the status of this is. So as many of you know, string theory in ADS3 cross S3 cross T4 is dual to a two-dimensional conformal field theory living on the boundary of ADS3. And this two-dimensional conformal field theory is a conformal field theory that lives somewhere in the moduli space that also contains the symmetric orbifold of T4. That's the old folklore of ADS3 CFT2, as already pointed out in the original Maldacena paper. Now, what's the analog of free super Mills in this context? Well, the very natural idea is that the analog of free super Mills is the symmetric orbifold theory itself, i.e. the theory that is really the symmetric orbifold of T4, rather than some other CFT that is on the same moduli space as the symmetric orbifold of T4. Because you see, this is basically 4n free fermions and free bosons modulo some global conditions. So that's basically a free theory. So our idea is that this should be dual to some special tensionless string dual. And the idea is that what this should mean, if you believe that it could be described among the string theories that has pure Navier-Schwarz background, then you would think it should correspond to the background with a minimal amount of NS and S flux. And that theory has a description in terms of the hybrid formalism of Berkowitz, Buffer, and Witten that involves a Wess-Lumino-Witten model based on the super Lie algebra PSU 1,1/2 at level 1 if k is equal to 1. Now, what's special about that theory is that this special super affine-Kac-Moody algebra has actually a free field realization in terms of free fields, namely symplectic bosons, and I'll explain to you later on what that means in detail, and free fermions. And what we checked is that the physical degrees of freedom of this worldsheet theory, once you include spectral flow, as we know, one has to when one describes string theory in ADS3, reproduces exactly the single particle spectrum of the symmetric orbifold theory. So the spectrum of the dual CFT is exactly accounted for by this worldsheet theory. So so this is the story for ADS3 cross S3, where we have checked many things, and I'll briefly review it in the following. But our basic tenet is that somehow the story for ADS5 cross S5 should work similarly. So what we propose is that dual of free n equals to 4 super-Mills should also be characterized by a free worldsheet theory. And the free worldsheet theory should be one where instead of PSU 1,1/2 at level 1, we'll have PSU 2,2/4 at level 1. The simple reason being that the zero modes of the super affine-Kac-Moody algebra will be the global symmetries of the dual CFT, and PSU 2,2/4 is the superconformal symmetry of n equals to 4 super-Mills. So that seems like a reasonable idea. And then you realize that this has a free field realization in terms of fields that look very similar to the fields that appear in the twistor string that Berkowitz proposed many years ago. So that seems like a very good starting point. You make contact with the twistor string, and at the same time, you manifestly produce the correct symmetries to correspond to the dual CFT. Now, the key ingredients, as for the case of ADS3, are spectrally flowed representations, and I'll explain to you in detail later on how they come about. But the upshot is that there is a natural quantization. We haven't understood all the details of it, but there is a very natural idea of how you should quantize this theory, and it leads to what we call a reduced model. And this reduced model reproduces exactly the single particle, that's a single trace spectrum of free super-Mills in the large n limit. So this is showing that what we believe to be a good sign that we are on the right track. Okay, so this was the brief overview on where we want to go. So let me now try to review briefly what we know about ADS3, what we've learned about ADS3, and then I'll try to explain to you how the generalization to ADS5 will work. So the ADS3, I'll try to keep relatively brief because this really uses results that have been described at previous string conferences. So ADS3 cross S3, you can describe in terms of a RNS formalism a la Mendocino-Oguri, but there's also this hybrid formalism of Berkowitz, Buffer, Witten. And in that context, you have the super Lie algebra PSU 1,1/2 at level k, where k is the level of the SL2R in the NSR description of Mendocino and Oguri. And as I said before, we are interested in the regime where k is equal to 1. And then this has a free field realization. But to be precise, you don't get a free field realization for PSU 1,1/2. You get a free field realization for U 1,1/2. And that is in terms of what I called 4 symplectic bosons and 4 real fermions. So the 4 real fermions, you recognize this is just the standard fermions that you have. And what I mean by 4 symplectic bosons is what you may want to call maybe a beta gamma system of spin a half. These are boson fields, but they satisfy exactly the same commutation relation as the fermions satisfy the anti-commutation relation. Now, what you can easily show is that the bilinears of the suitable bilinears of these fields generate U 1,1/2 at level 1. And then in order to go to PSU 1,1/2, we'll have to gauge by some diagonal U1 field. And that's the diagonal U1 field by which we gauge in order to get PSU 1,1/2 at level 1 from U 1,1/2 at level 1. Okay, so that is the fields that our theory has. Now, these are free fields. So when you would naively ask, what is the representation theory? Well, you can either put them all in the Neveu-Schwartz sector, or you can all put them in the Ramond sector. And in fact, these are the only highest weight representations which this theory has. So the Neveu-Schwartz sector will not play an important role in the following. So let's concentrate on the Ramond sector. And it basically looks, if you picture it, it looks a little bit like that. So you see you have some ground states along which the zero modes move you up and down. And then you can, the negative modes, just generate all the excitation modes. And here I've put down L0, and I've called it L0 of tilde for reasons that will become apparent in a second. And I've included J30, which is the Cartan generator of SO2. And the ground states, they form what you would call the singleton representation of PSU1,1/2 if you think about them in terms of the PSU1,1/2 generators. Now, these are highest rate representations, but as we learned from the work of Maldacena and Guri, one of the key insights is that in order to describe string theory in ADS3, you can't just have highest rate representations for the ADS3 factor. And the reason is basically a simple one. You see, you have to have arbitrary excitation number to get a string spectrum, and therefore the L0 spectrum can't be bounded from below. And in this context, what it means, you need a theory that has an unbounded L0 spectrum so as that to satisfy the mass shell condition, you can still have arbitrary stringy excitations. Now, what they proposed is that the additional representations you need are most easily described in terms of spectrally flowed images of, in our language, this Ramond sector representation. So what this means is we think of this same space, and it's a standard representation with respect to the tilde modes, but then we use some automorphism to write, to express the tilde modes in terms of untilde modes, and the untilde modes differ from the tilde modes only by virtue of the fact that their mode numbers are shifted up and down by W/2 in such a way that the commutators and anti-commutators are preserved. And then the idea is that you take this one and only representation with respect to the tilde modes, and you interpret it as a representation with respect to the untilde modes. In particular, the PSU1,1/2 generators, including L0, well, L0 isn't strictly part of PSU1,1/2, but it's part of the Rosseau algebra, you can work out. And what you find is that in this space, L0 looks as such, and in particular, the states with L0 equal to 0 are the states along this line. So what you recognize in particular is that you have all these states here below this line, and obviously this continues ad infinitum, that have a negative eigenvalue of L0. So the L0 spectrum is unbounded from below. And what you've done by this spectral float trick is to produce a new class of representations that are not highest rate anymore. And that's what you need in order to get a sensible string spectrum. Okay, so that's basically just reviewing Maldacena Guri in this context. Now, what's special about PSU1,1/2 at level 1 is that it has many, many null vectors. And one way to think about it is, you see, it has 4 symplectic bosons, but then you have to impose this U1 condition. And this U1 condition basically kills 2 bosons. So out of the 4, you only retain 2, but then you also have to impose the physical state conditions, as you always have in string theory, that will also eat 2 bosonic degrees of freedom. And what you learn is that there are no degrees of freedom surviving from the ADS3 × S3 factor. And all that you left over is the T4 factor. And if you analyze it, what you find is you get the symmetric orbifold of T4, exactly the single particle spectrum of the symmetric orbifold of T4, where the W cycle twisted sector of the symmetric orbifold comes from the W spectrally flowed sector on the world sheet. And this is something Lawrence talked about at Strings in 2019. So this is as regards the spectrum. Let me also briefly mention that the correlation functions of the symmetric orbifold theory are reproduced on the world sheet, and that comes from a remarkable property of the world sheet correlators. So the Z's are the coordinates, the usual coordinates on the world sheet, and the correlation functions on the world sheet have the remarkable property that they are delta function localized. So they're mostly 0, except at isolated points where they have delta function support, and they're localized to those configurations that admit a holomorphic covering map, i.e. a map from the Z's to the X's, such that Zi gets mapped to Xi plus a correction term of the order Z minus Zi to the Wi. This is a very restrictive condition, and as a consequence, you get a discrete sum over delta functions localizing to these covering maps. Now, the nice feature or property of that is that if you then do the modular integral, these delta functions guarantee that you only get a finite sum. You get a finite sum over the covering maps, and that basically reproduces the structure of the symmetric orbifold correlators. And thereby you see that manifestly our worldsheet description gives rise to the correct correlators of the symmetric orbifold. And this is something Rajesh talked about at Strings last year. Okay, so this is my lightning review of ADS3, and now we want to generalize this to ADS5 and basically take the same building blocks and try to modify them so as to fit the ADS5 cross S5 case. So our working hypothesis is that what we should do is we should start with 8 symplectic bosons and 8 real fermions. And as I'll explain to you, they'll generate U2,2/4 at level 1. And then you have to divide by some U1. And then you get P as U2,2/4 at level 1. And that basically guarantees you, as I said before, that you get the correct space-time symmetry. So what does this worldsheet theory look like more concretely? So we have to have 4 plus 4 symplectic bosons. So we organize them in 2 pairs. So there's a spinor index A alpha and a spinor index alpha dot. So we have 4 that are 2 doublets under alpha, 4 that are 2 doublets under alpha dot, and they satisfy the symplectic boson commutators as we had before. And then we have 4 fermions that sit in the fundamental and anti-fundamental representation of SU4, and they just satisfy usual fermionic anti-commutation relations. So that's our proposal, and as I mentioned before, that looks very, very similar than the field. In fact, it's essentially the same field content as the twistor description of Berkowitz. Now, the bilinears, when you take one generator out of the Y's and one generator out of the Z, they generate U2,2/4 at level 1. And in order to reduce this to P as U2,2/4 at level 1, you have to gauge by an overall U1 field, and the overall U1 field you have to gauge by is this diagonal version. That's the generalization of what we saw for P as U1,1/2. In fact, this construction is something that's also not that surprising, because this is really the affinization of the standard oscillator construction of P as U2,2/4 that appears in the standard spin chain discussion. So in the spin chain discussion, you would just look at the zero modes of all of these fields. You would do exactly the same thing. You would get P as U2,2/4. Here we use at the full non-zero modes, and you get the affine version of P as U2,2/4, namely P as U2,2/4 at level 1. Now, as for the case of ADS3, all the non-trivial aspects will come from spectral flow. Now, for ADS3, I said you have to shift the mode numbers up and down. And what distinguishes whether you shift them up and down was the eigenvalue under J30 minus K30, where J30 is what becomes the conformal dimension in the dual CFT, and K30 is the Cartan generator of SU2. Now, for ADS5, the natural analog is that you should take the dilatation operator to replace the conformal dimension and some asymmetry generator to replace the corresponding Cartan generator of SU2. So that determines how you spectrally flow these different fields. And then we do exactly as we've done before, except here it's convenient to start from the Neveu-Schwarz sector representation, but that really doesn't make such a big difference. So we impose that the tilde positive modes, the half modes and higher of the tilde modes, kill the ground state, and then you translate this into the untilde modes. And then, for example, this generator, the mu generator, will kill it, provided that R is greater or equal than W plus 1/2. That's the condition for all those that get shifted upwards, namely these guys. And for the other one, it's shifted downwards. Okay, so these are the generators that kill this ground state after spectral flow, but we have a free theory. So all those that don't kill create. That's the rule of a free field theory. So simply the complement of this set will freely generate the Fock space acting on this ground state. So if you think about it, from the first line, you get everybody where R is less or equal than W minus 1/2. And from the second line, you're going to get everybody where R is less or equal than minus W plus 1/2. So everybody will generate where R is less or equal than minus W plus 1/2. And in addition, from the first line, you get generators that lie inside this wedge between minus W minus 1/2 and plus W minus 1/2. Now, this is the worldsheet theory, and so far we haven't done anything unusual, but now, unfortunately, unlike the situation for ADS3, where we had Berkowitz-Waffer-Witten, who told us what the correct physical state condition is, now we're a little bit on our own. So what's our working hypothesis? So for ADS3, the physical state condition was that the physical states are primary, or the critical states of an n equals to 2, the states of an n equals to 2 critical string. Now, our worldsheet theory is basically twice as supersymmetric because it has twice as many symplectic bosons and fermions, and therefore it definitely has an n equals to 4 superconformal symmetry. And what we want to propose is that the correct physical state condition is that you impose the n equals to 4 critical string. Now, exactly how these n equals to 4 critical string generators look like, we haven't quite worked out, but we think that's a plausible assumption. Now, n equals to 4 algebra has 4 bosonic and 4 fermionic generators. So if you impose that the theory is critical, you kill 8 bosons and 8 fermions. So you would think you kill everything there is. And we want to take this to mean that we kill all the out-of-the-wedge modes. All of these out-of-the-wedge modes will be non-physical by virtue of this n equals to 4 critical string condition. Now, the remaining modes we want to think of as being some generalized zero modes. So in particular, we want to think of them as one copy from the two. So we have left movers and right movers, and we want to postulate is that one copy of these left and right movers survive after imposing the physical state condition. So you kill all of the out-of-the-wedge modes and you keep one copy of these wedge modes. And there is some intuition that this behaves similar to these U1 flux solutions that, for example, Dolan and Goddard wrote down for this Berkowitz string theory. So we believe that is sort of the natural analog of what we are doing here. As a side remark, we've also checked this for ADS3, where we have a more first principles derivation of what the physical state condition is, and we also land on our feet in that context. So that's what we propose. We propose you keep one copy of these wedge modes, and then you still have some residual gauge conditions, which come from the fact that we've forgotten about the fact that we are dealing with PSU 2,2/4 rather than U 2,2/4. So we have to still impose this condition. And we have a mass shell condition, which we take to be of that form. The idea here being that the ground state has the same charges as the BMN vacuum if you identify P plus with W. And then if you take the BMN formula and work at a tensionless limit, then you would think that 2p minus is an integer. So that suggests that this is L0 being equal to an integer times W seems to be the right sort of residual mass shell condition. Anyway, that's what we propose. At the moment, that's a proposal. We don't have a first principles derivation of it. Now, if you take this, then we can show that the resulting spectrum reproduces exactly that of free superangles in the 4D planar limit. So how does this work? Well, you think of these wedge generators as being momentum modes, and you do an inverse Fourier transformation to turn them into position modes. So you have W of these momentum modes. After Fourier transformation, you end up with W such position modes, and they pairwise commute if they sit at different positions. And then the residual gauge condition that Cn is equal to 0 for all n greater or equal to 0 translates into the statement that at each side, you have to set the C correspond to 0. So at each side, you have basically a copy of the usual oscillator construction in the spin chain picture because you just have one generator, and you have to set C equal to 0. So what this means is that at each side, the states in the singleton representation of PSU 2,2/4 survive. You have W side, so you get the W-fold tensor product of the singleton, and then this just imposes cyclic invariance, and therefore you land on the spectrum of free superangles in the planar limit. More specifically, the states in the W spectrally flowed sector correspond exactly to the W letter words, where you see, so the singleton representation has one state for each of the fields of superangles and its derivatives. For each element here, you have a state in the singleton representation. You take W many copies of those, and then you take the cyclic combination that survives in the trace. So that's exactly what the W spectrally flowed sector gives you. So in particular, you reproduce exactly the spectrum of free superangles. And what it suggests is that this is some sort of string bit picture, where in this W spectrally flowed sector, we have W string bits, but the string bits are twistor valued. They take values with these variables Y and Z, unlike what maybe one may have thought of originally. So this is our basic result, that upon this natural generalization from ADS3, we end up with a worldsheet theory, which admittedly there are some hoops and loops we have to jump over, leads to a spectrum that's exactly the spectrum of free superangles. So I try to convince you that the free field realization of ADS3 that is directly dual to the symmetric orbifold of T4 suggests a natural generalization to ADS5 cos S5. Then we've made some assumptions about what the structure of the physical state conditions will amount to. But if you take them, if you accept them, then we can show that the resulting spectrum is exactly that of free superangles in 4 dimensions. And therefore, this theory has a chance to be an incarnation of what we're looking for, namely a theory that describes free superangles. And it's again a free worldsheet theory that therefore fits the bill of what we were looking for. Now, obviously, there are many open questions and things we need to understand better. So first and foremost, we have to understand this physical state condition from first principles. At the moment, this is a bit of an inspired guess. Then we would like to study the correlation functions on ADS5. So remember, the correlation functions from ADS3 have this delta function localization property. And this came all from the Ward identity of the symplectic boson fields. So you would expect that something similar will happen for ADS5. And that ties in with what you expect the worldsheet correlation functions that are dual to free superangles to look like. Once we understand the correlation functions, obviously you can start to analyze the perturbation away from the free case and thereby really test this further and see whether we also produce the correct anomalous dimensions. Now, there are also more conceptual problems that would be interesting to understand. In particular, there should be a higher spin symmetry. We see this, but it's not manifest on the worldsheet. Only PSU 2,2/4 is manifest. There's obviously a Youngian symmetry in the spin chain that should have some implications here. And this suggests novel ways of looking at the spectrum and looking at correlators, and it would be interesting to relate this to other approaches in the literature. But my time is up, so I'll stop here and thank you for your attention.
Thank you. You finished just on time, so. Okay. Ofer Haroni has a question.
Hi, Matthias. I'm not sure if I completely understood how you think this physical state conditions would come from first principles. So I assume you want to have some n equals 4 superconformal gravity on the worldsheet or something like that. Or sorry, it was n equals 4 supergravity on the worldsheet. But then on top of that, do you want to just add a single U1 field, or do you need to add the full n equals 4 multiplet of the U1 field? Or what's the picture for where it would come about?
Well, so the picture is that we are, so in the ADS3 case, you have an n equals to 2 algebra, n equals to 2 superconformal algebra, which you build out of the free fields and the ghost fields of the Berkowitz-Waffer-Witten construction. Now here we want to construct a corresponding n equals to 4 algebra out of the symplectic bosons fermions together with the ghost fields. And then we are going to impose that, that the physical states are the critical states of this n equals to 4 theory. Now, that's just, so that is basically all there is, except that once you removed all the negative modes and you're looking at the zero modes, on the zero modes, you still have to impose some residual gauge conditions. So this condition will not just produce the zero modes. For example, the zero modes don't respect this PSU 2,2/4 constraint. C is not equal to 0. So this condition, some analog of that condition you will still have, but this is only on this wedge modes. This is only the leftover piece on this wedge mode. And likewise, there's a zero mode condition coming from the stress energy tensor. This is some sort of residual gauge condition after the heavy lifting has been done by all the n equals to 4 fields. So this is our picture, but admittedly, we haven't worked this out from first principles.
Okay, the next one is Shota Komatsu.
Yeah, well, actually I had the same question as Ofa, but I can ask a slightly different one. So is there a kind of way to say topologically twist the theory and reduce it to string theory in lower dimensions?
Sorry, say again. I mean, this is meant to be the full string theory. This is not
right. But like, let's say we are interested in more like a restricted sectors. Or put in another way, like, is there any relation between the ADS5 model and ADS3 model?
Well, I mean, in some sense, I've tried to convince you that there is a relation by this being sort of basically what you've done, you've replaced the T4 factor by another free field theory corresponding to. So obviously what you could do is you could try to sort of look at an ADS3 subsector inside it. You could also try to impose some additional topological conditions. Obviously, you could restrict on some sort of BPS sector inside it. That would be some additional cohomology on top of that. I mean, what we are reproducing is the full spectrum BPS and non-BPS of n equals to 4 supermills. So therefore, obviously, you could try to identify some topological subsector in here and identify what it means from the worldsheet perspective.
Okay, all right, thanks.
Okay, Igor?
Yeah, thanks for the interesting talk. Yeah, I couldn't follow all the details, of course, but I'm generally confused how a local, regular sort of worldsheet theory can describe weakly coupled gauge theory, because essentially the local worldsheet theory corresponds to only weak partons, only very soft partons, while in perturbative gauge theory, you have say, a lot of states where the longitudinal momentum, say, is divided between just a few partons. So if you, for example, just look at very naively what happens at weak coupling, you don't see the continuous sigma space that you see in standard worldsheet descriptions. Sorry if this is vague, but it's a general confusion I have. There has some miracle has to happen for a regular string action to suddenly describe free Young-Mills theory, beyond just the state production.
Right. So, I mean, obviously, what we'll have to do is we have to switch on the coupling constant. That's going to be a certain perturbation from the point of view of the dual CFT and a perturbation on the worldsheet. And then we'll have to see what happens to the spectrum. But I mean, the spectrum will stay intact. The question is whether we reproduce the correct anomalous dimensions. I guess our intuition is that it worked very naturally for the case of ADS3. And it combines various ingredients which people have seen in the context of what people believe could be the string dual of ADS5. But obviously, it may not work. But I think it has a fair chance to work. And I think that remains to be seen whether it will work out or not.
Okay, thanks. I'll think about it.
Okay, there's 3 more questions I'm going to allow, and then we're going to move to the discussion, and the questions can be moved to the discussion afterwards. So Mukund, you're next.
Thanks. Matthias, I'm confused about something. So I would have imagined that if you had tried computing the thermal partition function, you should see a Hagedorn transition here, which should correspond, which would be the free Young-Mills Hagedorn transition. But I'm then confused about the n scaling. Can you explain where the n scaling comes from in this?
Yeah, so that, I mean, we don't have, yeah, so I don't really have anything concrete to say about that at that stage. I mean, we don't have any temperature here. This is just at the free point, and we haven't looked into any of these questions in detail, so I'm afraid I can't say anything.
Thanks.
Shiraz?
Hi, Matthias. Thanks for the beautiful talk. Quick question. If I understood right, you've got a free field realization of your worldsheet field theory with n equals 4 superconformal invariance on the worldsheet and preserving this ADS5 times S5 symmetry in target space. Now, in order to turn on the coupling, this worldsheet theory, I suppose, would need to have a deformation that preserves these properties, right? That preserves n equals 4 on the worldsheet and the invariance of the target space. Is it easy to check is this the correct expectation, and is it easy to check whether it's true?
I think that's the correct expectation. Whether we haven't looked into it in detail, but the coupling constant is a deformation, so it should appear as one of the operators in our worldsheet theory, and therefore that's the operator by which you should perturb the worldsheet theory. And I think that has a chance to work, but we haven't tried to do that. We haven't tried to identify which exact vertex operator you would have to switch on the worldsheet in order to move you away from pre-super Young-Mills.
Thank you.
Okay. And the last question, Ed Witten.
Can you give us any kind of hint of what the n equals 4 generators are supposed to look like?
Well, I mean, obviously, out of the symplectic bosons and free fermions, you can generate an n equals to 4 algebra. That's pretty easy to see. But that's not the right n equals to 4 algebra, because you have to combine it with the ghosts, just like you did for the ADS3 case. So it'll be some combinations of the ghosts together with the symplectic bosons and the fermions. So what we do is we take the formula of your n equals to 2 generators, we write them in terms of the free fields at level 1, and then we are trying to generalize this to an n equals to 4 algebra. But we haven't found the right n equals to 4 algebra so far.
This n equals 4 algebra is supposed to commute with PSU 4/4, I assume.
Yeah, I mean, so to be honest, we have a little bit of problem understanding exactly how your construction commutes with all of PSU 1,1/2. It commutes with a large chunk of it, but we haven't quite understood how it commutes with all of it, but that would be our expectation, that the n equals to 4 algebra that we find will commute with the PSU 2,2/4 generators, yeah, the global symmetry.
Okay, thank you, Matthias. And then any other questions will be moved to the discussion section afterwards. And I think the discussion section is next.